No, now we're officially being recorded. To give a talk on natural language processing, and this format is truly a workshop, so we're not going to be digging into the innards of the individual models. Really, what we hope that you get away from this is, what does the data look like? What does the problem look like? What tool matches with the problem? And then how do I need to construct my data to be able to do anything about it? First of all, what is natural language processing? Some of you may have worked in this, maybe not, but really it's all about how a human and computer can communicate verbally through text, and having some form of language that they both can understand, having some sort of context. And the challenges in natural language processing are in speech recognition, which a lot of people have experienced. It's gotten a lot better recently. Natural language understanding, which is a little bit harder, meaning if you understand the parts of speech, but then actually understanding the context in which the speech is been written and communicated. And then natural language generation. We've seen a lot of that recently with some of the models that are starting to look like maybe they're actually thinking, but they're generating and writing books and articles and things like that. Okay. Real quick, some history is since there have been computers, there have been efforts in NLP. If you think about it, the human language obviously predates computational computer language. There has to be a bridge between there, but it started out as rule-based things. So maybe you could determine a certain form or if something was contained in text, but it really wasn't very smart. It was more of a really kind of logic-based rule system. In the 90s to 2010s, we started getting kind of the classical machine learning. So these would be random forest and Bayesian models to say, if say like in inverse term frequency, if you have a huge corpus of material and a certain word is contained within a document, that document actually should be the thing that is returned instead of some other document. Go back in time, you can do Google, and that was a lot of that was based on classical machine learning back at that time. Now everything pretty much is deep learning. Since 2015, pretty much all statistical models have been replaced by neural networks. I think what you'll see by the end of this talk is why that's the case. One of the areas that is certainly noted as potentially having the most benefit in these new, better understood deep learning networks is in medicine. And that's because we have decades and decades of notes and information about health. And without natural language processing, that kind of goes unused. So where's it used in medicine? So in some cases, to provide context, to understand a group of text, what context was it written in, what's some of the meaning in the text, and also generate appropriate text in a certain context to communicate with a person. A structure, and this is where a lot of people spend tons of effort, and that's taking and analyzing free text based on clinical notes and saying, is somebody healthy, not healthy? What's the prognosis? Is there any kind of predictions that can be made based on the free text alone? And more recently, interaction. We've all kind of experienced the phone call, press 1 or state what you want. Those were awful, even 4 or 5 years ago. Now they're getting a lot better. And Sam will have a little talk explanation on some of the chatbots that we've certainly done. So that's starting to become very useful in healthcare. But NLP, as I said, gives voice to unstructured data. We're not going to go through an individual model that actually have higher level libraries now that you don't even specify what model you're using. It will try to figure out which model that you would use based on the function. We're not going to go through the inside of the model and how it works, but the important thing to recognize compared to statistical models and other things, and even other deep learning methods like that, is that the reason that transformers seem to work so well on text is that they this idea of attention. And what attention really means in the most basic way is that it figures out a way to give importance to things that are important and diminish importance on things that aren't. So it isn't just statistically based on how many occurrences of something happen. With appropriate training, you figure out, well, that's an important thing, that's not an important thing. And it actually generalizes really well to a lot of problems. I mean, everything from analyzing images to playing video games, certainly in language. And one of the reasons that transformers have been so widely used in language is because they fine-tune very well. So you can take a model that's trained on all of Wikipedia and things, and it starts to learn, similar to vision models, it starts to actually learn the patterns of speech, the way that a certain language works. Okay? Then if you want to take and fine-tune that on a task of analyzing medical reports, pathology reports, radiology reports, you don't need a million records to do that. You can do a smaller subset. And what we'll talk about are a lot of the tasks that you can take these large language models and break those down into individual tasks. It's not there. Okay. What I want to get across for folks that maybe are younger or have not really been paying attention to the NLP space is that amazing things have happened. Important parts down here. Amazing things have happened in a very short amount of time. Meaning the human performance, you're starting to get models now. These are not my words. I don't really know what this even means. But models that are outperforming humans in reading comprehension and language understanding. That doesn't mean that it thinks. It means that at least on the tests that we have, they're having to rethink the benchmarks of natural language processing because the models are performing so well. So things are happening within the last couple of years that are really taking these tools and models, letting you do new things with them. The other trend that is happening is that the models are getting a lot bigger. So going back to just 2008, look at the model size in billions of parameters. There's a fraction of one. Now you've got 530 billion, and that's an active model that exists. I think recently the group out of China announced that they trained a 100 trillion parameter model. But not necessarily that's going to be better than the rest of these, but both in the volume of data and the parameters in the model, you're starting to see that bigger ends up becoming better. And that creates some interesting problems where if you don't have the appropriate computational infrastructure, you start not being able to participate in that. I forget how many thousands of hours it took for the latest GPT-3 and these other systems to train. You might know how to make this go away. Do what? Yeah. Oh. Deal with it. Maybe by the end we'll figure it out. Okay, this is what we'll go through is break down some of these tasks. See you back. Plenty of time. First task will be language modeling. That's the fitting of a particular language or domain-specific corpus to a model itself. And we don't really think of a vision model as that we don't normally think of vision models as training it for vision, although we use pre-trained models. But in this case, you're taking and adapting the model itself to the words and phrases that exist, not for particular tasks. We'll talk about that in a minute. Named entity recognition, that's assigning class to tokens, meaning to words or phrases. Okay, trying to pull things out of text. Sequence classification, generally broken down in sentiment analysis. Text classification, question answering, which is self-explanatory, and text generation. And that's what I said before, where you have these models that start maybe looking like they're sort of thinking. It's not taking and pulling text out of things it's been trained from. It's trying to understand the patterns of text and of speech so that it can create some relatively coherent text. Sometimes it does, sometimes it doesn't. Translation, which is self-explanatory. Speech recognition, audio classification, and image description. Image description is kind of on the cutting edge of this. I mean, you can provide an image and the model will explain what's in the image. Okay. First, language model. Has anybody done any language modeling in here? You know what that means? Sam, good. That's not enough. So language modeling, what you see here is that's fitting the model to the domain-specific corpus. And in our case, here's a list of scan, right, lip, punch, biopsy. So let's just say that we take the last 100,000 gross reports from pathology, which we've done, and we take that and we don't provide any labels. We don't do anything. We just have line with pathology reports. We're actually taking the model, training it on those individual inputs so that the model itself starts understanding the context of those reports. So in this, on the right-hand, see on the right-hand side, you can see that we in this case, you've actually masked or you've added tokens or terms to the model that didn't actually exist before. So it could be that inflamed may be part of the speech or bronchial. Maybe that existed before, maybe it didn't. And within this context, it actually has specific meaning. So that what we found, see this chart in the bottom, would be that models trained on, and it's not fine tuning, but models trained on specific domains outperform models that general purpose models. And it still work, the general purpose ones work. But if you want to get the best performance, you actually take the information, without any kind of labeling, and just run it through the model. Pretty easy to do. So I mentioned University of Florida. I mean, Florida's done a lot of amazing things recently. And one of the things that they are doing is training on, and I think there's going to be more explanation of this in with the next speaker, is that they are creating a what they call a Gatortron. In Gatortron, they trained 1 million patient records. So that's a language model that they've taken 1 million patient records to try to understand, to train the context of patient record information. Doesn't necessarily mean that it's fine-tuned to a specific test, but it is a model specific for medicine. And once again, they have a massive superpod that's 1,000 GPUs to do it. So when you start getting in this area, you have to be able to make some institutional investments to kind of stay in the game. Okay. Entity recognition. So this will be the first kind of fine-tuning test that we would talk about. This is assigning tokens or class to specific tokens. If you look on the right-hand side, you'll see this is also, I think, this would be a diagnostic type of report. So you're labeling procedure, 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 location, condition, location, condition. So those end up becoming indexes. So you're saying these phrases or these particular terms have some, they're entities. So if you're a database person, it's an entity of some sort. And those entities can be diseases, drugs, conditions, chemical parts, but you're trying to figure out from this unstructured text, how do I pull those things out? What you end up getting on that lower left-hand side would be that if you run that text, after you train your model, you run through that text again, you'll end up determining what index, what class it is, what string created that entity, or at least is being recognized as an entity, and the confidence score that it actually existed. You can imagine having, if you're looking for certain terms or certain entities and clinical reports, that this would be the way that you would extract those particular terms. We do it all the time for registries, trying to find location site, and people use it for all kinds of things. Okay. Next one would be 2 series of sequence classification, sentiment analysis. You see this all over the place. Here you typically take a base language model that understands some sort of form of text or language. Then you fine-tune that on a data set that will tell you whether something's, in this case, happy or negative or positive. It doesn't have to be negative or positive. It could be healthy, not healthy, or 3 or 5 classifications. In this case, what you would do is you'd have this language model, train it on, fine-tune it on something that says it's positive or negative, and then you would provide text. So in this case, I hate you, pretty positive that it is negative. I love you, pretty positive, positive. So this is used a lot in, at least in medicine, related to mental health or the state of a person based on what they're saying. There's another type of sequence classification, which is text classification. And this is a little different than named entity recognition, where you're taking the larger part of the maybe a whole phrase or sentence or paragraph, and you're assigning a certain label to that entire observation. So take a sequence observation or text, and then you say this particular label. Going back to our pathology gross cases, we've assigned a location type, meaning the anatomic place where that exists. And we get really good results for being able to pick out that anatomic location based on the notes alone. Okay? In some cases, they don't specifically have the term that is related to that location site. Question and answering, I'm going to skip this because it's pretty, somewhat skip it. The important part of this slide is that I'm not taking like a, we used to call them expert system and saying, here's the question, then return this answer. You're looking at blocks of text, and the model itself tries to figure out the context that it can be answered. So that taking this block of text, question, once again, is an NLP problem. What is an extractive question answering? It will tell me what it thinks the answer is, the confidence, and where in that text that it got that answer. So pretty interesting stuff going on there. Text generation. These are things that you've seen, especially these GPT models that they claim were trained on 45 terabytes of text and took months and months of training time. In this case, you just, once again, bigger is better. You're taking every kind of document you could possibly find and you're throwing into the model, and then you give the model a hint. And you're saying, based on this information, in this case, as far as I'm concerned, I will, then you don't spit out as much text as you want. We haven't gotten very far in this, but we're trying to look into this for pathology reports. We have a bunch of hematology reports that have gene and variant, and we have a bunch of associated text. So we think that that would be a good text generation to kind of pre-prepare written text based on those hints. In this case, the hint would be gene, variant, and the model would actually spit out the text. Translation, won't get into, that's pretty self-explanatory, but I will say that it's starting to become more interesting with some of the things that Sam's going to talk about, where you may be able to translate from one language, maybe to English, the inner workings of the model, or the virtual assistant work on English, and then it can spit it back out either through text or through voice, the other language. So fun stuff happening there. Same thing with audio speech. This is kind of pseudo NLP, but what you're doing is taking an audio wave. You're taking the digital captured voice, providing it to the model, and it's either doing speech recognition, which thanks to YouTube, it's probably in captioning on YouTube has been one of the biggest windfalls as far as this information, because for years and years and years, this was a really hard problem. Only the biggest companies had good models for language. Now, NVIDIA and other places have made, basically taken those training sets and made them available. So you take and have a particular point in time, and you say a certain word, and they can extract that word from the actual audio. The other thing you can do is audio classification. So if you had a phrase or something like that, it may be calm, neutral, sad. You're not looking for a word. You're just saying, in this audio, what's happening. And finally, image description. And this is where it's getting really interesting. And that would be if you have certain statements, certain text. In this case, you have a bunch of images. You can't do this with 100. Maybe you can't do it with 1,000. Maybe it takes 100,000. But you have certain statements about an image. Okay, that happens. You have enough of those and enough images. What you do is match up the text to the image. You're not annotating the image at all. You're just applying text labels to the image, and then you train it. And then after that, what you do is provide an image. Now, tell me the system to describe the image. This is a real thing. This isn't made up. You can go look at that particular project. The original report was heart size, pulmonary vascularity within normal limits. And the next one, the predicted text is that plus lungs are clear. So these are things that the machine isn't just pulling from a database or pulling text that existed before. It's looking at the image and trying to spit out the features that it has spotted in the image. Lots of interesting stuff in this area. Okay, well, my 20 minutes are up. You next or the other speaker? No, yeah, other speaker. I'm going to stop sharing, and then I think need Dr. Ju to share. Are you ready to go?
Hey everyone. Can I share my screen now, Nathan? Okay. Right. Can you see my screen okay? The slide?
Yes.
Okay, cool. Thanks for confirming. Hi, everyone. I'm Huiwen Ju. I'm a solutions architect at NVIDIA on the higher education research team. I'm focusing on helping researchers to adopt and leverage NVIDIA's technologies to accelerate their research. So today I'm going to introduce you some of the NVIDIA's fantastic technologies for NLP specifically. So my presentation for this part will just be 2 parts. First of all, I will introduce you to Gatortron, which is the world's largest clinical generative NLP models built by University of Florida and NVIDIA together. And then I will introduce you to NVIDIA NeMo, which is an open source framework for state-of-the-art conversational models. Okay, let's get started. So first, Gatortron. So Gatortron is a Megatron-based clinical language model. So you may be wondering what is Megatron? You've already heard that word from Cody's previous presentation too. So Megatron is a research framework for training a large language model, and it's a open source on a GitHub repo maintained by NVIDIA. So in that repo, we implemented all the kinds of parallelism mechanisms you will need to build and train and deploy your large language model. Actually, it's very complex, and yeah, it requires a lot of engineering expertise to build that research framework. And Megatron is mainly for researchers in this large language model area. Okay, so this Gatortron is pre-trained on the largest clinical data set ever assembled. So compared with previous state-of-the-art large language models in this biomedical and clinical area, for example, Biomegatron and also Clinical Bird, you can see here highlighted in green, Gatortron has been trained on the largest data corpus. And it has the largest number of parameters, which means it has it's much larger architecture. Okay, so this work has been done, and it's still continuing on University of Florida's SuperPOD architecture. So just like Cody just mentioned, they have over 100 DGX A100 nodes, and on those nodes, there are over 1,000 A100 GPUs. Yeah, so that's Gatortron. It's like a monster. It's taking a lot of GPU resources, keeping the SuperPOD busy all the time. Okay, then let's have a look at the performance of this Gatortron compared with other previous state-of-the-art large language models. You can see the size. Gatortron has the largest size. It has been pre-trained on so many different kinds of data sets. And you see for 2 common benchmarks for NLP models, Gatortron achieved the best performance compared with others. Yeah, so I think I forgot to mention, but Gatortron leverages this University of Florida, the medical school's tons of clinical nodes, and just like Cody said, they pre-train a model without any labeling, just throw out those data and then pre-train model, and then they fine-tune for those downstream tasks. Okay, but University of Florida and NVIDIA didn't just stop there. They have already done some further exciting work. So later on, we trained Syn Gatortron and Gatortron S, Gatortron synthetic. So what is happening there? Let's have a look at the diagram on the right. So what they're doing is that they're leveraging all the private UF health data and also some public data. And they use those data to train a generative model called Syn Gatortron. So that this Syn Gatortron can generate synthetic artificial clinical nodes. Okay, because we know clinical nodes just like any other medical data, privacy preserving is the biggest barrier for us to have access and to train a large model. So to overcome this problem, they train this same Gatortron to generate artificial clinical notes. Then after they generate those artificial clinical notes reports, they use that data to train another Gatortron architecture. And we call the previous Gatortron as Gatortron OG. And we call this Gatortron trained on those synthetic data as Gatortron S. And very excitingly, this Gatortron S achieved almost the same performance as this Gatortron OG. So here is the performance value for those commonly seen NLP downstream tasks, named entity recognition, relationship extraction, and also question answering, just like Cody mentioned before. So you can see Gatortron S achieves almost the same and sometimes even better performance. And NVIDIA has maintained those two models, their weights, the architecture in NVIDIA GPU cloud. So you can freely download that and then start from those already pre-trained model and then fine tune or do other tasks on your own data set. All right, so next I will introduce you to NVIDIA NeMo. It is a great toolkit for building your own state-of-the-art conversational models. Let's take a quick look at the stack of this toolkit on the right. So at the bottom level, there is CUDA accelerated libraries to give you the best performance running on NVIDIA's GPU. Then one layer up, NVIDIA NeMo is based on top of PyTorch and PyTorch Lightning. So if you have already got your training loop written in PyTorch or PyTorch Lightning, you will get seamless integration into NVIDIA NeMo framework. And then upper level. So in conversational AI models, a typical conversational AI pipeline, typically it will include more than one models. Like for an end-to-end conversational pipeline, sometimes we'll see people first use a ASR model, which means automatic speech recognition, and then get the outputs and then input that into an NLP, natural language processing model, to really understand what the input is. And then we send the processed data further to this TTS model, which means the text-to-speech model as an output. So, to put all those different kinds of models together within a single pipeline, it's not an easy job. However, NVIDIA NeMo can make it an easy job for you to do. So everything is modularized, and also it has automatic error checking for you. Okay, so on top of those three categories of models, we also released pre-trained models for each of those type of model, so that you can start from there instead of spend a lot of time to train your own pre-trained models. And also we provide sample applications for those conversational AI applications. Okay. Now here is just a slide to show you for all three types of models, what kind of tasks they're suitable for and their current accuracy, the performance, and also the pre-trained models. So we provide a lot of links so that you can just go to the NVIDIA GPU cloud called NGC, and then just pull up those pre-trained weights. Okay, now let's dive a little bit deeper into NeMo to see some very cool features from this NeMo framework. Okay, so with NVIDIA NeMo, you can enable mixed precision training and distributed learning, distributed training on NVIDIA's GPUs pretty easily. So GPUs are very sensitive to the precision you're using for a model, and using automatic mixed precision, like this technique will automatically detect which part of the model can be trained with lower precision so that you can further speed up your training. And also you can totally take advantage of NVIDIA's Tensor Core part on the GPUs. And distributed training is also necessary for training large language models. It's not that easy to do by yourself, so using NeMo can save you a lot of efforts. And also, I just want to point out, it's really easy to train within NVIDIA NeMo framework. Just with these 3 lines of code, you can start training. So the first line is to initiate a trainer instance, and then the second line, you just define the model you want to use. You don't have to write from scratch. All of those basic neural network architecture are already implemented within NeMo. You just call it and then parse it a configuration file to further define your model, and then trainer.fit, and you can start to fit your model on your own data set. And we already got a lot of tutorials. So if you click on that, you will be directed to this page. There are so many tutorials for different types of applications. And what is even better, so that, for example, I just click on this tutorial, ASR, automatic speech recognition with NeMo. You can see all of those tutorials can be run on Google Colab, which means you can start from today, try it out in your own web server. You don't need to have a powerful GPU or a workstation in your office. So what you have to do is just to change the runtime to GPU, and then you can start to click on those button and then run those cells one by one. They have a lot of explanation there. You will learn a lot from those descriptions way. Okay, so it will show you how to download some sample data set and then help you to explore those data sets, take a look at the data sets, and then it will show you how to give you some intro to the state-of-art models. And then it will show you how to train from scratch or fine-tune your model. So yeah, so it's very easy to just try out on yourself. So I just want to point out, remember I just told you there are just 3 lines of code. So this is the first line, this is the second line, and then, we start training third line. So really I recommend you to have a look. Right. Keep going. Okay, so within this NVIDIA NeMo framework, we also have a sub-framework, I'd say. It's called NeMo Megatron. So this is designed specifically for training large-scale NLP models. So now I'd like to elaborate a bit on large language models. So recently, we see those large language models are really performing well, and people have already invented new algorithms to pre-train a model and then leverage them for all different kinds of downstream tasks without fine-tuning for each of those downstream tasks. Popular algorithms like zero-shot learning, few-shot learning, like just Cody mentioned, you don't have to label your large corpus of data. Okay, they can just learn the structure, the pattern within those corpus. Yeah, so one single pre-trained model, they can serve all use cases for different downstream tasks. Yeah, so compared with traditional NLP models, recent large language models have much more parameters. It's much larger. And then, however, it's very powerful. It has a general understanding of your corpus. And they almost never need to be retrained or just need to be retrained minimally compared with the previous generation. Like they have to be retrained frequently for their task-specific training data. Okay, however, training and deploying large language models is not for the faint of heart. It is very challenging. So here on the left side, we listed the commonly seen challenges. Okay, so like for example, you have to process large-scale data before you train on those data, right? It's already a huge challenge. And then once you start training your model, it's very hard to find the most optimal hyperparameters, how to tune them. Is there any methods to help us to do that? And also large language models is different from other deep learning models in that it's very hard to make them converge, and also how to scale not only on cloud, but also how to scale on your multi-GPUs or on your multi-GPU nodes. And further, once you have a mature model, how can I deploy it in a robust way for inference and deploy it at scale? So all kinds of challenges, not to mention it will require a lot of expertise, and also it's very expensive to train a large language model from scratch. Okay? Tens of millions of dollars for this large model. Okay, now NeMo Megatron comes to help with all those kind of challenges. So here is just showing you the stack. So it provides a lot of great features. For example, it helps you to do distributed pre-processing for your giant data sets, data cleaning, right? And then it provides a method for you to do hyperparameter tuning to find the most optimal combinations for those hyperparameters and help you to navigate your own model. They are huge, right? And then help you to trigger distributed training easily on multi-GPU and on multi-node. And then furthermore, it can help you to do very fast, almost real-time inference with NVIDIA's technology called Triton. So yeah, so it helps you to address all those previous problems. Okay, so I just want to mention in this large language model area, we see a popular training strategy called prompt learning strategy. It becomes very popular. So on the bottom right, I just steal a figure from one of the main publication in this area. So you see for traditional model tuning strategy, we have a pre-trained model. And then for each of the downstream tasks, we need to fine-tune that model for each of those downstream tasks, which means for each of those ABC downstream tasks, we will have to maintain this large model. And then when we are going to do inference, like get outputs, get prediction from those models, we need to do those inference on each of those separate models, and it creates further like complexity layer for us to deploy and maintain those models. However, in a prompt tuning setting, we just need to have one pre-trained model, and we don't fine-tune for each of those ABC tasks. We just train some task-specific prompts embeddings for each of those tasks. And those embeddings are much, much smaller compared with this pre-trained model size. So when we are training it, we freeze our foundation model, or the pre-trained model, and then we just fine-tune further, or say further tune on those prompts, task-specific prompt, and create that prompt token embeddings. Okay, that way we just save a lot of time instead of fine-tuning those large ones, which will cost maybe weeks or months. We will just get very good outputs just by doing that. Okay, yeah, so here is what NeMo Megatron is bringing value, you know, for all those kinds of challenges. We have a solution for that. Okay, now let's jump back to the NeMo, larger, higher level. NeMo Megatron is just one sub framework. Okay. So once you've trained a model within this NeMo framework, it's very easy for you to export your mature model into this River framework. So River is a framework from NVIDIA to help you deploy state-of-the-art speech or conversational AI models. So when deploy that, you will need to leverage NVIDIA's like Triton to get you the best inference performance. Okay. I think I heard from Cody, later speakers might present a chatbot work that's already going on in your medical center, and that chatbot is leveraging River. Okay. NVIDIA NeMo also gives you several tools to help you clean your data, create your data set, and then explore your data to know more about your data. Okay, I'm coming to the final slides of this presentation. So here are some useful links for NeMo. If you're interested, you're welcome to check it out. And also specifically for NeMo Megatron, we also have a lot of resources created. And I just want to mention NVIDIA has a deep learning institute hosting a lot of self-paced courses and also instructor-led workshops. So I picked two, which are most relevant to our NLP topic. So if you want to learn more about how to build transformer-based NLP models using NVIDIA NeMo, you're welcome to register for that course, and also how to build and deploy large neural networks in general. We also have a course for that. It's an instructor-led workshop. Okay, I'm coming to the end of my talk. Thanks for your attention, everyone. Any questions?
Dr. Zhu, we have 20 minutes at the end for a question.
Okay, cool.
That's okay with you.
Yeah. Thanks. Okay.
Thank you. All right, can everyone in Zoom hear me?
Yes, I can hear you.
Maybe not. So I hope so. All right. So I am Samuel Armstrong. I'm a graduate student in the CS department, also a software engineer researcher in the Institute for Biomedical Informatics. Today I'm going to be presenting a demo of what we've been working on, virtual assistant that leverages Riva as well as Raza, an open source free chatbot system. So I'm kind of going to zoom through the slides because a little long. Don't have a lot of time. Anyway, so why do we need virtual assistants? So the main answer is to remove the human aspect from data collection. So if you have a research study and you have, 100 participants, it sucks to keep interacting with these participants on like an hourly, daily schedule. So that's where virtual assistants can really help. They can do automatic collection, stuff like that. And then also if you're doing, a million of these reports and stuff, it can lead to, fatigue, misinterpretation, and then, leads to collection errors. And then also manual reporting, at the end of the day, you want to report these to whatever research study you're doing. It wouldn't be fun. So virtual assistants can obviously do automatic reporting with that. So virtual assistants in the past. So this is a Forbes article that I found. So 86% of consumers prefer humans to chatbots. I'm sure everyone here in previous years have had experience with, customer service on the phone, and it's just press 0, give me the operator. I don't want to talk with this guy. So those were more than likely rule-based decision trees. So like Dr. Bumgardner said, 90s into the 2000s are all rule-based if then else statements. And then in 2010 and 2012, when Siri and the Google Assistant were released, that kind of re-sparked an interest like publicly, where virtual assistants can be used to further have conversations, stuff like that. So kind of zoom through this. So here's the market share. This is a 2019 market share of virtual assistants. So obviously you got some big players here: Amazon, Microsoft, Google, IBM, and then Raza is another smaller company. But it's important to see that all the big tech players have a hand in virtual assistants. Like there's no lack of need for this. So anyway, I'm gonna kind of skip through this because, as a researcher, using, just trying to develop something to get it out there, I don't want to pay anything for a virtual machine or a virtual assistant. So Google and Dialogflow are obviously paid by request, by text request, by minute or second of audio. And then Microsoft, IBM are free, but you have, let's see, as long as you stay below 10,000 predictions a month, you should be good. But the Microsoft one limits you to 5 transactions a second, which really isn't enough if you're doing like a research study with 100 people. Texting it at the same time, it won't work. So that's where Raza came in. So Raza is free, open source on GitHub, unlimited transactions, because you're really running Raza like on a server locally, anywhere you can put it. So this is how the demo is going to work today. So again, leveraging NVIDIA Riva. So like Dr. Ju said, there's a few parts in Nemo that are transitioned over to Riva. So you have ASR, automatic speech recognition, and TTS that we've used. And then instead of using NLU, we decided to use Raza. Well, we started with Raza and then built these NVIDIA components on the end. This is still in development also. There's also another technology called NVIDIA Audio to Face. So that will be added on to the end after the TTS. The TTS will input the audio file into Audio to Face and have a face, like a animated face, speak the text. But that's still in development. Other than that, I guess we could just go ahead and do the demo. So this is backup just in case the actual thing doesn't work. So everyone pray for a live demo.
Can we share the screen?
Yes, I do. Thank you. Okay, I think we're good. Alrighty, so we made this chatbot, well, not this specific chatbot, but these chatbots to aid in a research study that we have for the fasting app. If anyone was at the poster competition, my colleague Aaron's poster described it pretty well. So we have a bunch of participants texting into us when they're starting to eat for the day, and then when they finish eating. So they can say, basically what they want to say is start cow and then a time, but we want to have them be able to say, I am starting to eat now, basically. So we're going to have Raza in this chatbot flow in front of behind the text messaging service, but in front of our state machine moving code. We can talk about that later in the discussion. All right, so let's just get into it. This is a blood glucose reporter type thing. like I said, everyone pray. I'm ready.
What is your name?
Sam,
What is your blood glucose reading? Go.
65.
Your blood sugar is low. Take steps to raise it. Have you exercised today?
Absolutely not.
Is your stress level low, medium, or high?
It is pretty high,
Have you been drinking water?
obviously.
Would you like a healthcare professional to call you about these results?
No, I don't think I need that.
Okay, great. Here's your daily wellness log. Name, Sam, blood glucose, 65, exercise, no, stress level, it is pretty high. Drinking water, yes, contact from healthcare professional. No, thank you for your time. If this form looks correct, then you are done. If you need to make corrections, type or say redo.
So let's verify that it actually got the right thing. So 65 and no. I know 65 got it. Absolutely not. Pretty high, obviously. So see, I mean, Raza does a pretty darn good job of determining intent. Obviously, this is not scripted. I'm just making these up as I go. And if you don't believe me, I'll be here all day. We can go through this together. So this is just kind of where we're going in the medical realm, I guess, with our stuff. So yeah, I just also at the very end, I just want to show how easy it is to set up a Raza thing. So once you download, install Raza, you run command line Raza space init, and it generates these 8 files. So your main files here are the domain here. So these are all YAML files. It's pretty easy to define intents. So like if user says like no or something, you want to have it'll match to deny. And these are slots for all those question answer things. Let's see. Here's all the responses that it can say, and then also it stores all the slots in memory, so you can access them whenever. Pretty cool. Yeah, and then one other. I'm just gonna go through this quickly because no one wants to look at code. So here's basically how you define an intent. You give it a ton of examples, and then you let it train on. I trained this one on 100 epics using the diet classifier and a white space tokenizer, I think. And then, yeah, you really don't need a whole bunch to determine, an intent. But I just thought I'd show it because it's kind of interesting. And then last thing, go away. Last thing here is that Raza's also has an API endpoint. So you can also do form validation. So what I'm doing here is every answer that the user says, it gets validated to make sure it's the right intent, 2, in a format that I want it to be in, and then don't have it saving to a database, but this would also be where you'd save it to a database to use for later. So we got a lot of Python stuff here. But yeah, I think that's all I have to talk about. Does anyone have questions? Because I guess we can do the.
Just leave your computer connected, and I think we can open up for any questions about either one of the conversations. We've got until 10:15 before our break. So I think in this case, any of the speaker questions or the main intent of this is to kind of go through from a high level. These are the things we have. These are how they work. More importantly, this is what the data looks like if you have a project that you want to do. So the data looks like, this code looks like, using tools. So this is an opportunity to do 2 things. 1, ask questions of the speakers, and 2, start think about and talk to your collaborators. And Nathan, maybe you can shout out for the folks online if they have any questions. What projects do you think that we could do now that you've seen these things? Are there things that you think we could do here? So let me start with questions of the speakers.
And talking to you as well. So what is the final deliverables for data from the University of Florida health system? Because there need to be departmental specific, like say in pathology, digital pathology, in radiology, they will say somebody is going to be reading the images and then come to the physician.
So what they talked about in the large, and maybe Dr. Chu can say better than I do, but maybe my simplistic understanding maybe helps understand better, is that the model itself can be adapted towards certain patterns of speech. So you see these large models that are trained on Wikipedia and movie databases. They don't necessarily work. They don't work as well in the medical domain as things bring to the medical domain. So what they've done in Florida is they've taken, I think they said over 1 million of their clinical notes and I guess 299 million other PubMed articles and things like that, that use the same type of speech that you see in the medical domain. So what that means is that that is an underlying large language model, which then you would have a better, probably better performance adapting to that pathology than just a general purpose model. So if we wanted to take something like I said before with the genomic reports, we'd start with a big Gatortron model that has a medical domain knowledge, then fine tune it to a specific task that we were interested in. So reports related to genomics or even reports for grossing or final diagnosis. And even if it had to do with describing the image, we could start with that base model first. Is there any other comments? That makes sense. Okay. And what else? Anybody want?
Yeah, I have a question. So,
Yeah.
Regarding something related to feature with Professor and the SAM's demo, so we have 3 parts with the ASR, NLP, and the TDS, right? I feel like at SAM's we have been working with the ASR and the TDS, and you are relying on the machine-based in the middle. So I'm wondering, so regarding the 3 parts, which parts are the most suitable? I mean, configurable for our medical.
Well, configurable. I'll start with the core. The core of these things, if you imagine you have a research study or a program or anything that you want to repeat, would be the core protocol that you want to do. Okay, so this must happen, this must happen, this must happen. So for computer science, that would be considered a statement sheet. So some of us have been on projects where we've had rule-based things, and then you record the data, and if something doesn't work, the investigator comes back and said, well, this person submitted something at 10 o'clock, but I didn't see it at all, or I saw it too. Going back and looking at those database tables and the code and trying to figure out what happened, when it happened, is an absolute nightmare. So out of our own pain, there's a tool called UMPL that lets us describe states, turns it into a graph that you can go and get back to the investigator and say, is this the protocol that we're trying to follow? Then we'll generate some template code. So at the core of these things, we end up with something that is systematic, mathematically verifiable, that it will work and it'll do the thing that it'll transit. As long as you do state transitions correctly, it'll work. What we're bolting and layering on top of that, the same can explain that, would be these other tools. So maybe you can from the core up.
Yeah, so we have UMP at the core, right? And then so whenever a user texts in, obviously it needs to be determine the intent. So that's what we're using Raza for. So then Raza sends a request to UMPL or an API, a Java wrapper that's around UMPL, to move the state in the appropriate way. So what we're trying to do here is have a pretty human-like conversation to, move an actual computer component. So
I think the only thing that we did, the ASR is something that's provided by NVIDIA, the TPA is something provided by NVIDIA. The rest of those tools are provided by Raza as a framework that's provided by them. We have a configuration for the state machine, and we have configuration for Raza, and that's basically it. So that you take the same framework and you can do how many ever conversation bots that you want, taking advantage of that.
We have more valuable intelligence.
Yeah.
Right. So there's in Raza they have a model called Spacey, SPACY, and that one you can use specifically for medical termination or terminology. So yeah, it's kind of cool.
So what projects do you think? Are there anything you can think about with your own work or even patients or your experience as a patient, are there any things for any of these areas where natural language processing or a chatbot or any of these things would be useful? We can talk about that in this context. Yeah.
Cody, sorry. I think that I'm going to talk my talk really, because we need a lot of clinical information and to interpret the genomic data, especially exome sequencing. And the process to grab those ICD-9 code HPO terms, it is really, first it's painful, second is incomplete, and third, depending on a good mood or bad mood of the day, because I'm reading the thousands of notes. So, in that way, is there a way of like AI or learning process that can objectively go to the medical record? Now it's it's accessible, it's Epic, and then extract those HPO terms as the first step, and second, make sure it's really sift out all those, like say if a genetic patient like 5 years and there's last 3 years there are a couple hospital visits, just common cold or fever, this is nothing related to genetic, and sift those out. That's really something helpful for genomic part.
Yeah, it's hard. It would be hard to fathom how much money has been spent over the last 20 or 30 years by NIH and NLP to do HBO and other term extraction, and it's just now gotten very, very interesting. So the last 5 or 7 years that the deep learning has kind of taken over. So yeah, what you do is have your notability, and for those what we're talking about is HBO, is human phenotype ontology, is the name of it. And it actually can be used in variant ranking when they have 50,000 variants and you want to try to be done. It can actually predict the variants. So you need the clinical notes, but it's really painful to go and read through somebody's history. It's not like you're just provided to go and feed into the algorithms that then will do some of the ranking for you. So yeah, 100%. There are lots of projects out there to do. When we talk about name entity extraction, those would be terms that then go to those ontologies. And so that's not something we necessarily have to build. We can use some things that are already out there. What we would do is we had access to the notes just through the Epic API. We would take and pull whatever notes we could find from a person, run them through the named entity extraction with HBO terms, and then we would have that list that then we feed off. That's something that's completely doable, real. We do it right now. Yeah. So we'd have some tests with that, but we never had access to the data, clinical data, to actually run it. So we had the extractor set up, just not the data. Yeah, definitely. So we can do that. Yeah. The other thing that I've thought about, and this has to do with schedules, is that in the clinical lab, there's something called critical values. So an analyst sees a critical value that is, for whatever reason, it's something that's critical to the patient. They stop what they're doing, then they start trying to call people to find the person that is responsible for that person's care. Then they have to find them. Then the person has to accept the value, which is accepting responsibility to say this is happening. Perfect solution for something like this. If we had access to what physician or what provider was related to that patient, we can do it all day. We can do it through text, we can do it through voice, we can do it through phone, fax, whatever it happened to be, and pretty confidently have that person accept it, and do this without having to take the technician out of the.
That's exactly, because I think that now this Epic is much better because we can use instant text. And first, we need to call the station, the doctor is not on site, and transfer to a different person. That person needs to read it back. So it's just like, I think the process can be much faster and much secure.
So what Sam has already done is that we have methods that already go through text messaging system. If we had a bot that was inside of Epic, we had an API access to say this is the clinical lab bot. It could use the existing Epic messaging system to say, have that same conversation. This is critical value for this patient, and send it directly to a person within the system. You accept, type back the number, you accept this, and then we'd be able to report that in audit. So it doesn't really matter to us at the core what methods we use to communicate.
We have a question in the chat here. So question is, how robust is the speech recognition to accents, and does it support other languages? So I'm going to answer the second question first. Other languages, Riva has Spanish, English, Chinese, Russian, and one more where you can speak to it and it can or not translate, but write down the text in whatever language it is. However, the text-to-speech part can't speak it in the language that it comes in. So there's only English out. So that's kind of a problem that we're, I guess, kind of waiting for NVIDIA to release an update. So, but other than that, the first question, so robustness to accents. So I actually have a problem when saying sure. It can't pick up like S-U-H-R or S-U-R-E. It picks up S-H-O-R-E. I guess I have the twang or something, but it's not super robust to accents. We haven't tried it with a whole lot of different ones, but it's good enough, but it can definitely use work.
What I would say is if you use any speech to text things in the previous 7 years ago, it's like wizardry. So it's going to take somebody that has a heavily thick accent. My wife's from Missouri, she can understand that. But anyway, so it probably does as well as not white in terms of the accents. I think that also has to do with a lot of what's going on in AI is making sure that you have a diversity of people and accents and things, and these models are getting a lot better. I think in general, pretty good for some question and answer.
Oh yeah.
Hey, what else? We got 4 more minutes. What's a project we could do? So we got for your young friends.
So in terms of security and authentication, can you add something like the authentication by people who are access or speech recognition?
I haven't thought about it, but maybe.
I think in the demo you have presented, the patient has to self-check if the record is correct. And I'm thinking that intelligence can be built in to recognize the speech, the patient that speaks.
Right.
Something.
Yeah. So the demo I have is just you don't have to ask like the name and stuff. And the output at the end is just to show that it's saving the entities. But so how it's authenticating right now is so you have to log into this website and it's using your link blue as like a session basically. But using actual voice to like doing that, I'm not aware of anything that can do that with NVIDIA or Raza. So
Yeah, it's probably similar to like facial recognition. It's certainly doable. We haven't had a reason to do that. On the other projects we have cell phone numbers because the interaction is text-based instead of audio chat. But doable. I mean, matter of fact, if it's when you bring the face on, you could actually confirm with the face or the voice. Yeah, I think it's doable.
We got another one that says, "Is this HIPAA compliant?" I have no idea.
Everything is compliant.
Yeah.
Yes, you could be made HIPAA compliant because that's another important aspect. Kayla and I have worked on some stuff that were based on Alexa. We did some stuff with the city. And then we started looking at AWS. We were trying to use those Alexa services, which goes off to the cloud, and then they weren't HIPAA compliant, and they didn't do real well in the healthcare sector. Because Raza and all of these things, everything that we showed can be deployed locally, they're not cloud-based, then we can make it as secure as you want. So it doesn't have to go out anymore. And that's kind of the amazing thing. Before, the really good services would have to go out to some service someplace, and that was problematic, both from a functional standpoint, because maybe the network didn't work. We can't quite put this on a Raspberry Pi type of system, but it's certainly getting. Okay. Anything else before we get a break? Well, if you want to get with one of us, and you can text Dr. Ju and Sam, and if you would think of any projects that you'd like to do, same thing with the upcoming things. So just kind of make a mental note. Hey, it would be neat if we could do this. This would be really helpful quickly. Then we'll get our list of projects, and then we typically what we do is say this is our wish list. If it's something that we can try to turn out to do demonstrations very quick, either get funding or to try to do it from a clinical side, go and find out where the gaps are in the technology data. That's part of the reason we're here. So, we break. Okay. So we'll do a break. There's still breakfast, water, and the next session, which is 10:30, will be Dr. Justin Miller, and that'll be in bioinformatics. And Kaylin and Huiwen, all of you.